This is a demonstration of my audio-visual interactive art piece. The theme for this piece is noise, and as I'm about to demonstrate, noise has been incorporated throughout the work, not only in the form of sound, but also noise as in random fluctuations in data. So if I start by pressing the keys, each key will play its corresponding sound and indicate the last one that has been pressed visually. And you'll notice as you start playing the notes, the more sound you make, the more of this pattern is drawn in the display area. Switching over to amplitude now, when you turn it on, this shows the amplitude history as a graph above the last notes played. Switching over to frequency now, this will turn off amplitude and instead display the frequency of the note being played, with the low end on the left and the high end displayed on the right. Switching both off again, you then are left with a blank canvas and can start drawing again. So how does this all work? The piano and buttons work very simply. The keys are drawn using a for loop that divides the canvas width by the desired quantity of notes, and then drawing rectangles until they reach the canvas width. The black notes work in the same way, except the maths is changed to centre them between the white keys and to leave a gap at specified increments. Then, if the mouse is clicked within the X and Y boundaries of the rectangle location, it will execute the relevant function to either play the sound or change the scene in the case with the buttons. When clicking the black keys, obviously the coordinates overlap with the white keys, so the white keys always contain an if statement specifying to do nothing if a mouse click occurs within the black key boundaries. The click will also trigger button color and text to change, or for an overlay to display on top of the key to indicate which was last pressed. Once the button is pressed, the amp function is called, the amplitude level is read, and that data is then stored in an array. Then, using a vector, we start drawing a shape to graph the amplitude data. The x position of the vector is determined by two things, the amplitude level and the center location of the last note pressed. If the amplitude is 0, the x position of the line is at the center of the last note. If the amplitude is at maximum level, the graph peak is 50 pixels to the left of the key center. The y position of the vector is a visual representation for the index position in the array storing amplitude history. So for as long as there is level history data being fed into the array, this will increment through the array one position at a time, while simultaneously moving down the y-axis by 1 pixel per index position. When it reaches the top of the piano keys, using the splice function, it will delete the data point at the start of the array and add the new data to the end. This will then stop it from drawing on past the keys and eventually off the page. For frequency, this functions similarly to the amplitude function, but this time the amplitude level is being analysed per frequency band across a spectrum. The data for each frequency band is then stored in an array, and then each data point for that array gets translated for visual representation as the height of a rectangle. Each rectangle represents a frequency band going from low to high, from left to right. So, as you can see, higher notes have more activity in the higher frequency bands, providing a visual representation of the maths behind how a piano works. Finally, for the drawing that occurs when neither buttons are selected, this is primarily not my code, as it's a bit above my skill level. I just modified it so that it would work with my project and appear to react to the sound, which is achieved simply by changing the stroke width according to the amplitude level. I'll still explain how it works anyway to demonstrate understanding. Essentially what you are seeing is the individual paths of 600 particles, or whatever quantity specified within the program, all with physics applied to them as they flow through and interact with an invisible grid of vectors, which are all constantly changing their angle according to Perlin noise. Perlin noise is a random sequence of numbers where each number has to relate to the one that came before it, giving randomness that flows smoothly. So when applied to this vector field, each angle has to correlate with the angle of the vector in the adjacent cell, giving a nice pattern and creating a flow field. If you make these vectors visible, they look like this.